October 1995. A small observatory in the south of France. A 29-year-old doctoral student named Didier Queloz is staring at a set of numbers that do not fit any model he trusts. He has been running the same calculation for hours. The data keeps returning the same answer. A star called 51 Pegasi, about 50 light-years from Earth, is being pulled. Something is tugging at it. Something with enough mass to make a star wobble. That part is not unusual. Planets pull at their stars. That is actually how we find them. You watch a star. You measure the tiny back and forth motion caused by something orbiting it. The technique works. What does not work is the number Queloz keeps getting for the orbital period. 4.23 days. He checks it again. 4.23 days. Whatever is pulling at 51, Pegasi completes a full orbit in 4 days. Not 4 years. Not 4 months. 4 days. On Earth. A year is 365 days. Mercury, the closest planet to our Sun, takes 88 days to complete one orbit. And Mercury is already considered extraordinarily close. But this thing, whatever it is, finishes an entire trip around its star in 4 days. That means it is not just close to its star. It is almost touching it. Queloz calls his supervisor, Michel Mayor. They go through the data together. They check for errors. They check again. The number does not change. What they are looking at, if the data is right, is a gas giant the size of Jupiter, sitting closer to its star than any planet in our solar system has any right to be. The heat alone should have disrupted it. Every formation model anyone had ever written said something like this could not be there. And yet, Mayor and Queloz published their findings in October of 1995. The reaction from the scientific community is not celebration. It is stunned silence, followed by a wave of attempts to find the error in their work. There is no error. 51, Pegasi b, is real, and it changes everything. Queloz later described the discovery not as simple excitement, but as a specific kind of disbelief, the kind that keeps you checking the same result again and again, not because you think you made a mistake, but because you cannot reconcile what the data says with everything you were trained to expect. That feeling, that specific collision between what we expect and what is actually out there, is what this story is about. Because 51, Pegasi b, was only the beginning. In the 30 years since that night in France, we have confirmed more than 6,000 planets beyond our solar system. We have found planets covered in oceans of lava, planets where the weather is made of iron and glass, planets being slowly consumed by their own stars, planets orbiting 2 suns at once, planets drifting through the galaxy with no star at all, and planets circling the dense, spinning remnants of stars that exploded billions of years ago. Each one of them rewrote something we thought we understood, and each one forces the same question. A question that gets harder to dismiss the more planets we find. What if Earth is not the standard? What if everything we assumed a planet is supposed to be, everything we learned from living on this one world, is just a local habit the rest of the universe never agreed to follow? This is what the universe actually looks like when you stop expecting it to resemble home. Close your eyes and picture the solar system. You already know what it looks like. You have seen the image hundreds of times. A bright sun at the centre, 4 small rocky planets clustered close, a belt of asteroids, then the giants, Jupiter and Saturn with their rings, Uranus and Neptune in the cold outer dark, everything in its place, everything following a logic that feels almost architectural. Rocky planets near the heat, gas giants far from it, a natural progression from small and dense to large and diffuse, arranged as if someone had planned it that way. That picture is real. Our solar system does look like that. The problem is that we spent centuries staring at it and made a mistake so fundamental, so quietly embedded in everything we taught and assumed, that most people still have not noticed. We mistook the local example for the universal rule. When astronomers began finding planets around other stars in the 1990s, the assumption going in was straightforward. We would find systems like ours, maybe slightly different in scale or timing, but the basic architecture would hold. Rocky planets close in, gas giants far out. The model would be confirmed. We already had the perfect template. What the data returned instead was a catalogue of violations. The first thing that shattered the template was hot Jupiters. Gas giant. Some of them larger than our own Jupiter. Sitting in orbit so close to their stars that a full year on their surface lasts just a few Earth days. The first one Kellos and Mayer found, 51, Pegasi b, was a Jupiter-sized world completing an orbit in 4 days. When more surveys came back with similar results, it became clear this was not a fluke. Hot Jupiters exist in significant numbers. They just do not exist in our solar system. And no one had predicted them. The formation models had always said gas giants cannot form close to a star. The heat is too intense. The stellar radiation would blow away the gas before it could accumulate into a planet. Gas giants had to form in the cold outer regions where ices could condense, where building material was abundant, where a planet had the time and the raw material to grow massive enough to pull in a hydrogen envelope. That is where our Jupiter is. That is where the model said gas giants had to be. But hot Jupiters were close in. Very close in. If they could not form there, they had to have formed further out and moved inward. The picture of a static, orderly solar system where everything forms in place and stays there was wrong. Planets migrate. They interact with the disk of gas and dust around young stars, lose orbital energy, and spiral inward. Some of them drift enormous distances from where they were born. That revelation alone restructured decades of planetary science. Then came super-Earths. A super-Earth is a planet larger than Earth but smaller than Neptune, rocky or partly rocky, not a gas giant, not a terrestrial planet in the familiar sense, something in between that our solar system does not have a single example of. And surveys of the galaxy revealed that super-Earths appear to be among the most common kinds of planets our instruments can detect. Systems with 1, 2, 3 super-Earths are everywhere. Our solar system has none. Sit with that for a moment. The most frequently detected type of planet in the galaxy is a type we have never lived near, never had as a neighbour, never had any direct experience of. Everything we know about planets comes from a system that skipped that category entirely. Close behind super-Earths in frequency are mini-Neptunes, worlds between the size of Earth and Neptune, gaseous or ice-rich, with no sharp surface, also extraordinarily common in exoplanet surveys, also absent from our own neighbourhood. The picture that emerged from the first decade of serious exoplanet discovery was not a confirmation of the solar system as universal template. It was the opposite. Our solar system began to look like an outlier, an unusual configuration, a place that happened to turn out a certain way, but not the way most planetary systems turn out. There is a term from linguistics that captures this well, a local accent. Every region develops its own way of speaking the same language. The accent sounds normal to the people who grew up with it. It is not universal. It is just what the language sounds like in that particular place, shaped by history and geography and circumstance. Our solar system is a local accent. It is what a planetary system sounds like around a star like our Sun, in this part of the galaxy. After 4.5 billion years of a specific gravitational history, it is real. It is Ors. But it is not what most of the galaxy sounds like. And when you start learning the other accents, some of them are almost unrecognizable. The Kepler Space Telescope, Lagotchine 2009, and operational until 2018, surveyed over 500,000 stars and found thousands of planet candidates. The statistical picture it returned was unambiguous. Planetary systems are everywhere. They are diverse in ways we had not anticipated, and they cluster around types and configurations that our own system barely represents. Here is the thing that took years to fully sink in. We did not just find new planets. We found out that the frame we were using to understand planets was too small, built from one example, applied to an entire universe. And the universe, as it turned out, had not been consulted. Every chapter ahead is an example of what the universe chose to build when it was not following our local rules. Some of them are extreme in ways that feel violent. Some are strange in ways that are almost beautiful. And some of them are so far outside anything our experience prepared us for that the word planet starts to feel like a courtesy we extend out of habit. The map we grew up with was not wrong. It was just drawn from a single point. And we forgot to mention that part. Picture a year that lasts 30 hours, not 30 days, not 30 weeks, 30 hours. You wake up in the morning, you go through your day, you have dinner, you fall asleep, and by the time your alarm goes off the next morning, the planet you are standing on has already completed one full trip around its star and started the next year. That is not a thought experiment. That is the actual orbital period of a planet called WASP-12b. WASP-12b is a gas giant, roughly 1.5 times the size of Jupiter, orbiting a star about 1,300 light-years from Earth. It completes one full orbit in 1.09 Earth days. To put that in terms of distance, it sits less than 1/40th of the distance that separates Earth from our Sun. Mercury, the closest planet in our solar system, orbits at roughly 4/10ths of an astronomical unit. WASP-12b orbits at about 0.023 astronomical units. It is not just close to its star, it is practically inside it. At that distance, the dayside atmospheric temperature reaches somewhere around 2,250 degrees Celsius. That is hotter than the surfaces of some of the coolest stars in the galaxy. And temperature is not even the most dramatic thing happening to this planet. The most dramatic thing is what the star is doing to its shape. When a planet orbits close enough to its star, the gravitational pull on the near side of the planet is meaningfully stronger than the pull on the far side. That difference in gravitational force across the diameter of the planet is called a tidal force. On Earth, tidal forces from the Moon are what cause ocean tides, a gentle daily rise and fall of sea level. Manageable, predictable, something you can set your watch to. On WASP-12b, the tidal forces from its star are not gentle. They are strong enough that the planet is no longer a sphere. It has been pulled and stretched into an egg shape, with one end bulging toward the star and the other end trailing behind. The planet is being physically deformed by gravity in real time, and that is still not the most alarming part. The star's gravity is pulling material off the outer atmosphere of WASP-12b and drawing it into a disk of gas that spirals inward toward the star itself. The planet is leaking, measurably, observably, in ways astronomers can detect in the data. Depending on the model, WASP-12b may have only a few million to around 10 million years left before it is consumed entirely. A few million years sounds like a long time. It is not, by cosmic standards. Our sun has been burning for 4.5 billion years. The dinosaurs went extinct 66 million years ago. Whatever is left of WASP-12b when it finally disappears into its star, the timeline is closer to the age of early human ancestors than to the age of the solar system. By the standards of the universe, this planet is already in its final chapter. We just happen to be watching. This is what hit differently when Kellos looked back at 51 Pegasi b after the field exploded with discoveries. That first hot Jupiter, the one he found in 1995, sits at roughly 1/20th of an astronomical unit from its star, completing an orbit in 4 days. The planet that launched the entire field of exoplanet science was itself a world under constant assault from its own sun. Every hot Jupiter we have found since has the same fundamental story. Close orbit, extreme heat, a star that is slowly winning. WASP-17b adds a different kind of impossible to this picture. It is a hot Jupiter with a retrograde orbit. Most planets orbit in the same direction their star rotates. Because both the star and its planets formed from the same rotating disk of gas and dust. Everything inherited the same angular momentum. Everything spins the same way. WASP 17b goes around its star backwards. The leading explanation involves a close gravitational encounter with another massive body early in the system's history. An encounter violent enough to flip the planet's entire orbital direction. A near miss that reversed the travel direction of a world larger than Jupiter. The fact that such an event is possible, let alone that we found a planet where it apparently happened, is a useful reminder that solar systems are not born orderly. They are born chaotic. The order we see in mature systems is what survives after billions of years of collisions, migration, and gravitational near misses that occasionally go very wrong. Or in WASP 17b's case, go backwards. What makes hot Jupiters matter beyond their individual strangeness is what they revealed about planetary formation itself. Before their discovery, the assumption was that planets form where we find them and stay there. The solar system looked like a stable, static arrangement. Hot Jupiters proved that planets move. They migrate across enormous distances. They interact with each other and with the disk of material around their young stars. They can end up in orbits that are nothing like where they began. That meant our solar system's architecture was not inevitable. Jupiter did not have to end up where it is. The orderly system we live in is one outcome among many possible outcomes, shaped by a specific gravitational history that could have gone differently at multiple points. We got lucky with the arrangement. WASP 12b did not. And 30 hours from now, wherever it is in its orbit right now, it will be back where it started. Another year completed. Another fraction of its atmosphere pulled into the disk that is slowly returning it to the star it was born around. Think about the ground beneath your feet right now. It is solid. It has weight and resistance. If you drop something, it would stop when it hit the floor. The ground is the thing that does not move. The thing everything else is measured against. It is so fundamental to physical experience that language built itself around it. We say things are grounded. We find our footing. We stand on solid ground. The ground is the baseline of reality. Now consider what happens when you take that away entirely. About 41 light-years from Earth, in the constellation Cancer, there is a world called 55 Cancri E. Its formal designation is 55 Cancri E. Astronomers who work with it sometimes call it Janssen, after the Dutch lens maker Zacharias Janssen, who is credited with an early contribution to the development of the telescope. The name has a certain irony. Janssen helped us learn to see things far away. And what we see when we look at 55 Cancri E is a surface that would make the concept of standing completely meaningless. 55 Cancri E is a super-Earth, about twice the diameter of our planet and roughly 8 times the mass. It orbits its star in about 18 hours, and at that distance, the dayside temperature reaches somewhere around 2,400 degrees Celsius. At 2,400 degrees, rock does not just melt, it vaporizes. The silicate minerals that make up the bulk of rocky planets, the same basic materials as granite and basalt, transition from solid to liquid to gas at these temperatures. Some models suggest that much of the dayside of 55 Cancri may be covered by an ocean of molten rock, not pools of lava in volcanic regions. An ocean, planetary in scale, deep, churning, superheated liquid rock as far as any surface extends. That alone would make it extraordinary. But here is where things become genuinely strange. Data from the James Webb Space Telescope suggests that 55 Cancri E has an atmosphere, not like any atmosphere in our solar system. The readings are consistent with gases actively vented from the molten material below, possibly including carbon dioxide, carbon monoxide, and silicon monoxide. Silicon monoxide is gasified rock. The atmosphere of this planet may contain materials that on Earth we would classify as part of the ground. On Earth, the distinction between atmosphere and geology is clear. The air is air. The ground is ground. They interact at the surface. Weather erodes rock. Volcanoes vent gases. But the categories are stable. You know which one you are standing in. On 55 Cancri E, that boundary has dissolved. The rock is in the air. The ground is in motion. And observations indicate that the thermal emissions from the dayside vary over time, which suggests the molten material itself is not static. It moves. It churns. It redistributes heat in patterns that shift on timescales of weeks or months. The ground, such as it is, never stops moving. A nearby world called K2141b takes this one step further. K2141b is a super-Earth orbiting even closer to its star. Its dayside temperatures are high enough that sodium and silicon monoxide may exist in gaseous form on the dayside. These materials, according to current models, get carried by high-altitude winds around to the night side of the planet, where temperatures are lower, and there, they condense. They fall. There is weather on K2141b. The term weather is doing significant work in that sentence. The thing models suggest is falling from the sky on K2141b is not water. It is not ice. It is vaporized rock that has cooled enough to shift back towards solid or liquid form. It is, in the most literal sense the physics allows, raining minerals. On Earth, the water cycle is the engine of weather. Water evaporates from oceans and lakes, rises into the atmosphere, forms clouds, falls as rain, collects in rivers and oceans, and evaporates again. The cycle runs on a substance that exists in all three states within the temperature range our planet operates in. K2141b may have a rock cycle in the same sense. Rock vaporizes on the dayside. It travels through the atmosphere. It condenses and falls on the night side. The difference is that the substance running this cycle is what we stand on, what we build with, what we bury our dead in. There is a concept in geology called the rock cycle. Rocks on Earth form, break down, get subducted into the mantle, melt, and eventually get pushed back to the surface as new igneous rock. The cycle takes millions of years and operates mostly invisibly beneath the surface. What worlds like 55 Cancri E and K2141b appear to have done is externalize that entire process. They may have taken the rock cycle and moved it to the atmosphere and the surface, where it operates not over millions of years but continuously, openly, as weather. When Queloz and Mayer confirmed 51 Pegasi b in 1995, what shocked everyone was the orbital period. The 4-day year. The proximity to the star, the idea that a gas giant could survive that close seemed impossible. But the deeper lesson, the one that took years to fully sink in, was that heat at those scales does not just make a planet warm, it rearranges what a planet is allowed to be. 55 Cancri E is the extreme version of that lesson. A rocky world. A world with mass and radius not so different from Earth's in principle, but one that orbited close enough to its star, for long enough, that the things we expect a rocky planet to have, a stable surface, a clear distinction between ground and sky, a geology that operates beneath your feet rather than above your head. All of it has been erased. What remains is not a failed version of Earth. It is something the physics always permitted, but nothing in our solar system ever produced. A world where the ground is the weather, where geology and atmosphere have merged into a single, continuously circulating system. The ground is the most basic assumption we make about what it means to be on a planet. On 55 Cancri E, that assumption lasts exactly as long as it takes the molten surface to remind you it was never standing still. Rain by definition, is something falling from the sky, on Earth. That something is water, the logic feels almost too obvious to state out loud. Clouds form when water vapor rises and cools. Water droplets collect around dust particles. They grow heavy enough to fall. They hit the ground. The cycle repeats. Rain is water. That is what rain is. The definition feels permanent, like a fact about the universe, rather than a fact about one specific planet in one specific solar system. It is a fact about one specific planet, 64 light-years from Earth. In the constellation Vulpecula, there is a world called HD 189733b. From a distance, it is one of the most visually striking exoplanets ever studied. It appears to be a deep cobalt blue, a colour that in photographs looks almost peaceful, almost familiar, almost like something you might see reflected in an ocean on a clear afternoon. The blue is not from water. It is from silicate particles suspended in the upper atmosphere. Silicates are the same mineral family that makes up most of Earth's crust. Quartz, Feldspar, the rock under your feet, on HD 189733b. Those minerals exist in the atmosphere as tiny glassy particles, smaller than a grain of sand, drifting through the upper layers of a gas giant hot enough to keep them permanently suspended. The planet orbits its star in about 2.2 Earth days. Its dayside temperature reaches roughly 1,000 degrees Celsius. Its night side is several hundred degrees cooler, which on this planet means it is still hot enough to melt, lead with room to spare. The temperature gradient between day and night drives winds. And here is where the numbers stop feeling like numbers and start feeling like something else entirely. Wind speeds on HD 189733b are estimated at around 8,700 kilometers per hour. The speed of sound in Earth's atmosphere at sea level is about 1,235 kilometers per hour. The winds on this planet move at roughly 7 times the speed of sound. They circle the planet continuously, carrying those silicate particles from the day side to the night side and back again in a relentless horizontal flow. At those speeds, the particles are not drifting. They are moving like projectiles. Silicate glass at 7 times the speed of sound is not weather in any sense that a living organism would survive. It is sandblasting on a planetary scale, continuous and uninterrupted, driven by a heat differential that will not change as long as the planet keeps orbiting where it is. The blue colour, the almost peaceful cobalt blue visible in telescope data, is what that looks like from the outside. From the inside, it would be a wall of glassy fragments moving faster than any hurricane in human history, beautiful and lethal in the same instant. But HD 189733b, for all its violence, is only the beginning of what atmospheric extremes can look like. About 640 light-years from Earth, there is a planet called WASP 76b. It is a hot Jupiter, roughly twice the mass of our Jupiter, orbiting its star in less than 2 Earth days. The dayside temperature reaches approximately 2,400 degrees Celsius, which is hot enough to vaporize iron, not melt it, vaporize it. At these temperatures, iron transitions directly from solid to gas, becoming part of the atmosphere on the day side. The planet is almost certainly tidally locked, one side permanently facing the star, one side permanently facing away. The iron vapour that forms on the blazing day side gets swept by atmospheric circulation toward the cooler night side. On the night side, temperatures drop enough for the iron to condense, to transition back from gas toward liquid droplets, and then, following the same basic logic as rain on Earth, gravity pulls those droplets downward. On WASP 76b, it rained iron. Observations made with the espresso spectrograph at the Very Large Telescope in Chile found signatures of iron vapour in the atmosphere on the day side of the planet. On the night side, those signatures were absent. The iron was going somewhere. The most consistent explanation is condensation and precipitation. The iron falls on the night side, rains down into lower atmospheric layers, and eventually the circulation carries the iron back around to the day side where it vaporizes again. The same cycle as rain on Earth. The same basic logic. Evaporation on one side, condensation on the other, precipitation downward. The physics is familiar, only the substance has changed. The James Webb Space Telescope has added another layer to this picture. Observations of a planet called WASP 94AB revealed something that until recently we could only model. Webb detected a difference between the morning and evening sides of the planet's atmosphere. The evening side, the edge transitioning from day to night, showed signatures consistent with magnesium silicate clouds. The morning side, transitioning from night to day, appeared clearer. What Webb was seeing was cloud formation and dissipation happening at different points in the atmospheric circulation. For one of the first times, we were not just inferring the existence of alien weather in general, we were distinguishing one side of a planet's daily atmospheric cycle from another, on a world hundreds of light years away. The fact that this is possible at all is one of the more quietly astonishing facts about where we are in science right now. The instruments exist, the data is real, and what it shows us is that weather, as a physical process, is not unique to Earth. What changes is the raw material. On a planet hot enough, the water cycle becomes a rock cycle. The rain cycle becomes an iron cycle. The clouds are not water vapor condensing around dust. They are magnesium silicates condensing around the same temperature gradients that produce cirrus clouds on Earth, just at temperatures and with substances that have no equivalent in the world that taught us what weather is supposed to mean. Weather, it turns out, is not about water. It is about phase transitions. Any substance that can shift between gas and liquid or solid under the temperature gradients driven by a star will form weather. The universe does not have a preference for water. It runs the same physical process with whatever material happens to be available at the right temperature range. On Earth, the available material is water, and the temperature range is between 0 and 100 degrees Celsius at 1 atmosphere of pressure. The result is oceans and rain and snow and fog and the particular way a summer storm smells before it arrives. On HD 189733b, the available material is silicate glass, and the temperature range is around 1000 degrees. The result is cobalt blue clouds and winds at 7 times the speed of sound, and a kind of beauty that exists entirely outside of anything a living thing could survive long enough to appreciate. The sky on that planet is gorgeous, and it would end you before you finished the thought. Everything in the last 3 chapters has been about extremes of heat and violence, planets being consumed, surfaces made of molten rock, skies that would destroy you before you had time to look up. This chapter is different. Not every strange planet is trying to kill you. Some of them are strange in a quieter way, a way that does not feel threatening so much as genuinely, almost philosophically baffling, a way that makes you reconsider the most basic assumptions, not about safety or survival, but about what it means for a large object to exist at all. Consider a planet called Kepler 7b. Kepler 7b is a gas giant. It orbits a star about 1,000 light-years away in the constellation Lyra. It has a radius about 1.5 times larger than our Jupiter, making it one of the larger exoplanets we have measured. If you placed it next to Jupiter in our solar system, it would look significantly bigger. Large things are supposed to be heavy. That is how matter works. Volume implies mass. Mass implies weight. Kepler 7b has a density of about 0.17 grams per cubic centimetre. To put that in context, water has a density of 1 gram per cubic centimetre. Styrofoam, the packing material used to ship fragile things, has a density of around 0.05 grams per cubic centimetre. Kepler 7b sits between those two. It is 1.5 times the size of Jupiter, and it is less dense than water. This comparison is strictly about density, not about a physical scenario that could actually occur. No ocean large enough to test this exists, and a gas giant would not behave like a solid ball dropped into liquid. But density comparisons are useful precisely because they show how alien the object is. When the density of a planet falls closer to styrofoam than to rock, the number has stopped behaving like a number that describes something familiar. TOI 3757b is even more extreme. Discovered by NASA's Transiting Exoplanet Survey satellite and confirmed in 2022, it is roughly the size of Jupiter but with a density lower than cork, lower than most wood, significantly lower than Saturn, which is already the least dense planet in our solar system. TOI 3757b makes Saturn look comparatively dense. These worlds are called superpuffs, which is the kind of informal nickname planetary scientists use when the formal terminology fails to capture the sheer improbability of what they are looking at. The question they raise is not just about density, it is about stability. What is holding these planets together? A gas giant like Jupiter has enormous mass, and that mass creates sufficient gravity to hold its atmosphere in a compressed sphere. Kepler-7b and TOI 3757b have far less mass relative to their size. Their surface gravity is weaker. The question of what prevents their atmospheres from simply expanding and dispersing into space over geological time is one that models are still working through. One leading explanation involves ongoing atmospheric escape. These planets may not be stable in the long term. They may be slowly losing material from their outer atmospheres, their upper layers expanding and leaking away under the influence of radiation from their host stars. What we are seeing when we look at a superpuff might be a snapshot of a planet in a particular phase of its life, inflated and diffuse, in the process of slowly becoming something denser as the outer layers dissipate, a gas giant slowly losing itself. Another explanation involves internal heat. Some hot Jupiters receive so much radiation from their stars that it heats and inflates their outer atmospheres, keeping them in an expanded state that would not persist if the planet were moved further from the star. The star is essentially holding the planet puffed up through continuous heating. Kepler-7b also became the first exoplanet for which astronomers were able to map the distribution of clouds across its surface, using reflected light data from the Kepler telescope. Observations showed that the planet reflects significantly more light from its western hemisphere than its eastern hemisphere. The interpretation is that clouds, likely made of silicate particles or magnesium compounds at high altitude, are concentrated on one side of the planet. One side is Claudia. We can see it from 1,000 light-years away. Something stops you when you sit with that fact. Not the density paradox, not the floating thought experiment, but the image of looking at a world 1,000 light-years away and saying with confidence that its western sky is cloudier than its eastern sky. The resolution of our instruments, the sensitivity of our telescopes, the mathematics connecting photons collected over years of observation to a statement about cloud distribution on a world across the galaxy. All of it is real and operational and producing results. The universe built a planet that defies our intuitions about what large things are supposed to weigh, and then it made that planet reflective enough that we could map its clouds from the other side of the galaxy. HAT P67b sits at a further extreme. It is one of the largest and most inflated hot Jupiters known, with a radius almost 2 times that of Jupiter, and a density so low it ranks among the least dense planets ever confirmed. It orbits its star in less than 5 Earth days. Its upper atmosphere is almost certainly losing mass at a significant rate. What you are looking at when you look at HAT P67b is a gas giant in the process of being slowly dismantled by its star. The star puffs it up and pulls it apart simultaneously, and the planet currently exists in this expanded, almost ghostly intermediate state between what it was when it formed and what it will eventually become. There is something quietly unsettling about that image that has nothing to do with violence or heat. We tend to think of planets as finished things, objects that formed, stabilized, and settled into whatever they are. The solar system presents that picture. Earth has been Earth, recognizably, for billions of years. Jupiter has been Jupiter. Superpuffs are a reminder that a planet can exist in a state that is not equilibrium, that a world can be in the middle of becoming something else. Slowly, over millions of years, without any dramatic event triggering the change. Just a star, doing what stars do, pouring energy into a planet that is not quite dense enough to hold itself together against that pressure. We call them planets. The classification is technically correct. They orbit stars. They have sufficient mass to be roughly spherical. By the definitions we use, they qualify. But when you look at the numbers, when you sit with a density of 0.17 grams per cubic centimetre, the word planet starts to feel like a very generous description of something the universe built in a moment of almost casual improbability. Not dangerous, not violent, just impossible in the way that a magic trick is impossible, where you know the explanation exists, but the image in front of you refuses to resolve into something that makes comfortable sense. The name sounds like good news. Super Earth, a bigger Earth, a more substantial Earth, a world with more of everything that makes Earth worth living on. More landmass, more resources, more room. The prefix super carries a specific set of associations in American culture. Superman, superstar, Super Bowl. When we put super in front of something, we mean upgraded, enhanced, better than the standard version. The name was not designed to mislead you. It is a size classification, nothing more. A super-Earth is any planet with a mass between roughly 1 and 10 times the mass of Earth, sitting below the threshold where a world becomes a gas-dominated mini-Neptune. The term describes size. It says nothing about surface conditions, atmospheric composition, gravity, temperature, or anything else that would determine whether a place is livable or lethal. But the name does its damage quietly, because when people hear super-Earth in a headline about a newly discovered exoplanet, the image that forms is not a technical size classification. The image that forms is Earth, but more, a second home, a backup planet, something waiting out there for us. That image is almost never accurate. Start with gravity. A super-Earth 2 to 3 times the mass of our planet would have surface gravity somewhere in the range of 1.5 to 2 times what we experience here. That does not sound catastrophic. It is the kind of number that invites the question of whether humans could adapt. Here is what that actually means in practice. At twice Earth's gravity, a person who weighs 150 pounds here would effectively weigh 300 pounds. Every movement costs more energy. The cardiovascular system works harder. The skeletal system carries greater load. Long-term exposure to significantly elevated gravity causes measurable physiological stress. Astronauts returning from 6 months on the International Space Station need weeks or months of rehabilitation to recover from the effects of low gravity. The transition in the other direction, from normal gravity to significantly higher gravity, presents its own version of that problem, and it does not get easier with time. Now add atmosphere. A more massive rocky world holds onto its atmosphere more tightly. That is what greater gravity does. En masse, which is smaller and less massive than Earth. The atmosphere is so thin that standing on the surface without a pressure suit would cause your blood to boil. The gravity is not strong enough to retain a dense atmosphere over geological time. On a super-Earth, the opposite problem applies. A larger, more massive world with higher gravity could accumulate and retain an atmosphere significantly denser than Earth's. The surface pressure could be crushing. The atmospheric composition might be rich in hydrogen or other volatiles that the planet held onto, precisely because its gravity was strong enough to prevent them from escaping. None of that is necessarily fatal on its own. But combine elevated gravity with high atmospheric pressure and a composition that did not evolve alongside oxygen-breathing life, and the word super in the name starts to feel increasingly ironic. Then there is the ocean question. GJ1214b is a world about 2.5 times the diameter of our planet, orbiting a red dwarf star about 48 light-years away. Its mass and radius measurements are consistent with a world that contains a large fraction of water, far more water by proportion than Earth, not an ocean covering 70% of the surface. A world where water may constitute a significant fraction of the total planetary mass. On Earth, the deepest point in any ocean is the Challenger Deep in the Mariana Trench, about 11 kilometers below the surface. The pressure at that depth is roughly 1,100 times atmospheric pressure at sea level. We have sent unmanned vehicles there. No human has descended to the bottom and back more than a handful of times in heavily engineered vessels. The ocean on GJ1214b, if models are correct, may extend for hundreds of kilometers in depth. The pressure at the bottom of such an ocean would be so extreme that water would no longer behave as liquid water. Under sufficient pressure, water can enter exotic phases that do not exist in any natural environment on Earth's surface. Forms of ice that remain solid at temperatures well above boiling point because the pressure is strong enough to force the molecules into a crystalline structure despite the heat. States where the boundaries between liquid and something else become difficult to define. GJ1214b may have an ocean, but the ocean on GJ1214b would be unlike any body of water on Earth. The surface layers might look recognizable, go deep enough, and the water itself becomes something that does not have a common name because no human has ever encountered it outside of a laboratory at extreme pressures. In 2023, the James Webb Space Telescope observed GJ1214b, and the results suggested an atmosphere with heavier compounds rather than light gases like hydrogen and helium. The exact composition remains uncertain. The picture is of a world that is genuinely complex, layered, pressurized, chemically active, and only beginning to be characterized. K218b occupies a different and particularly contested corner of this conversation. It is a mini Neptune rather than a strict super-Earth, sitting at about 8.5 times Earth's mass and orbiting in what is considered the habitable zone of its red dwarf star, about 120 light-years away. In 2023, James Webb detected carbon dioxide and methane in its atmosphere, along with a tentative signal that some researchers interpreted as dimethyl sulfide, a molecule that on Earth is produced primarily by marine phytoplankton. That last point generated significant media coverage about the possibility of life on K218b. The scientific picture is considerably more careful than most of those headlines suggested. The dimethyl sulfide signal is tentative and contested. The planet is a mini Neptune, which means it likely has no solid surface in the way Earth does. The habitable zone classification refers only to the range of distances from a star at which liquid water could theoretically exist on a surface. It does not account for atmospheric pressure, composition, or a dozen other factors that determine whether water actually exists in a usable form. K218b is a genuinely interesting target for further observation. What it is not, based on current data, is confirmed evidence of anything biological. What K218b demonstrates, whatever its ultimate nature turns out to be, is that the habitable zone is not a guarantee. It is a starting point for investigation. The super-Earth and mini-Neptune categories contain hundreds of confirmed worlds. Some of them are lava worlds. Some are ocean worlds with crushing pressures. Some have thick hydrogen envelopes that make their surfaces inaccessible in any meaningful way. Some orbit red dwarf stars and are likely tidally locked. The variety within the category is enormous. What the category does not contain, in any confirmed case, is a world that clearly resembles Earth in the way the name implies. The search for Earth-like worlds is still in its early stages. The tools required to characterize a rocky planet's atmosphere in detail are only now becoming available. James Webb is among the first telescopes powerful enough to begin probing the atmospheres of some small, nearby worlds in meaningful detail. The field is young, the data is accumulating, but the name Super Earth is not a promise. It is a measurement, and measurements. As Queloz knew better than most, I have a way of telling you things the names never prepared you for. A super Earth is a size. It is not a destiny. The universe is not building backup Earths for us. It is building planets. In the full, chaotic, indifferent variety that physics permits. Some of them happen to fall in a size range that sounds familiar. What they actually are requires considerably more than a name to understand. On Earth, every child learns the same basic fact about the sky. The sun rises in the east. It moves across the sky in a predictable arc. It sets in the west. Tomorrow it will do the same thing. The cycle is so reliable, so embedded in biology and culture and language, that we do not think of it as a feature of our planet. We think of it as a feature of reality. The sun rises. That is what suns do. It is a feature of our planet. About 245 light-years away, in the constellation Cygnus, there is a world called Kepler 16b. It orbits two stars, not one, Tfo, a primary star that is roughly 69% of the mass of our Sun, and a secondary star that is about 20% of the mass of our Sun. The two stars orbit each other with a period of about 41 days, and Kepler 16b orbits the combined centre of mass of both of them, completing one trip around the pair in approximately 229 Earth days. The confirmation of Kepler 16b in 2011 by the Kepler Space Telescope caused a particular kind of reaction in the scientific community, not just scientific interest, though there was plenty of that. Something closer to a shared recognition that a thing which had existed in imagination for decades had turned out to be real. Planets orbiting two stars had appeared in stories and films for a long time. The science on whether such orbits could be stable had been worked through theoretically, but actually finding one, actually measuring its period and mass and orbital parameters, produced a moment that felt different from a typical exoplanet announcement. The two-sun planet was real, and the reality of it is stranger than any fictional version. Consider what it actually means to have two suns providing your light. The two stars in the Kepler 16 system are different sizes and different brightnesses. The primary is an orange dwarf. The secondary is a red dwarf. When both are above the horizon, the light they cast is a combination of two sources with slightly different colours. The shadows they create are independent. At certain times, you would have two distinct shadows pointing in two different directions, each one cast by a different star, each one at a different angle depending on where both stars happen to be in their mutual orbits relative to where you are standing. Here is the part that takes a moment to absorb. Your shadow has a shadow. At other times, the two stars would be close together in the sky, nearly aligned, and your two shadows would overlap into something strange and compound, darker where they cross, fading at each edge. At still other times, one star would be below the horizon and only the other would be up, and you would briefly have a sky that looks more like a conventional single-star system. One sun, one set of shadows, one light source. Then the first star would rise again, and the doubling would return. The timing of all of this shifts over the course of Kepler 16b's year, because the positions of the two stars relative to the planet change as the planet moves through its orbit and as the two stars move through their own mutual orbit around each other. Predicting where exactly both suns will be at any given moment requires tracking three separate orbital periods simultaneously. The 41-day period of the two stars around each other, the 229-day period of the planet around the pair, and the relationship between those two cycles, which drifts continuously in a pattern that does not exactly repeat for long stretches of time. There is no stable season on Kepler 16b in the way Earth has stable seasons. Earth's seasons come from the axial tilt of the planet relative to a single sun. The relationship is consistent year after year. Winter is always roughly the same length as last winter. Kepler 16b's relationship with its two stars changes in a pattern that is periodic but complex, with the amount of light the planet receives varying depending on the relative positions of both stars. Some periods would be significantly brighter, others dimmer. The pattern repeats, but only over longer timescales than any simple season. Sunrise would not be a single event. Depending on the positions of the two stars, you might see the primary rise while the secondary is still below the horizon. Watch the sky shift as the secondary rises later, and then observe a double sunset where neither the timing nor the direction of either setting is the same as the day before. Two sunsets, in different directions, at different times, on the same evening. No 2 days would be quite the same. Kepler 34b and Kepler 35b, two other circumbinary planets confirmed around the same time as Kepler 16b, add further variations. Their host star pairs have different mass ratios and orbital periods, producing different lighting dynamics at every scale. In all three cases, the underlying principle is the same. Two gravitational anchors instead of one fundamentally changes the temporal experience of being on the planet, not just visually, seasonally, biologically, in ways that would reach all the way down into the daily rhythms of any life that tried to organize itself around those cycles. There is also something worth noting about where planets cannot exist in these systems. Circumbinary planets must orbit outside a certain minimum distance from the stellar pair to remain dynamically stable, too close to the two stars, and the competing gravitational pulls would perturb the planet's orbit into chaos over relatively short timescales. Kepler 16b orbits just outside that stability boundary. The margin is not enormous. There are regions in the Kepler 16 system where a planet simply cannot maintain a stable orbit. The competing gravitational forces of the two stars create zones where any object following a certain path will eventually be pulled into an unstable trajectory and ejected. These are forbidden zones, in the sense that the mathematics forbids stable orbits there, not because of heat or radiation or chemistry, because the geometry of two gravitational fields overlapping at certain distances produces dynamics that no orbit can survive. A different kind of strange from anything in the previous chapters. Not a planet being burned or stripped or crushed. A region of space where reality, operating entirely through basic gravitational physics, has ruled out the possibility of a stable world existing there. Some addresses in this solar system are just not allowed. The beautiful part remains beautiful. Two suns, two shadows, a sky that never repeats exactly the same way twice in a human lifetime, an entire relationship with light and time and the rhythm of days that is nothing like Earth's and is not worse for it, just different in ways that make every assumption about what a normal sky looks like feel newly provisional. Kellos spent years measuring stellar wobbles, tiny shifts in starlight caused by the gravitational pull of orbiting planets. The technique is precise. It tells you something is there. It tells you roughly how massive it is and how far it orbits. What it cannot tell you is what the sky looks like. The shadows on Kepler 16b have two sources, two different lengths, two different angles. Shifting together and apart across a sky that follows rules our solar system never had occasion to write. We found the planet with math. What it actually means to stand under that sky is something the math only hints at. Every culture in human history has organized time around the same event. The sun rises, the sun sets, day gives way to night, gives way to day again. The rhythm is so deep in human biology that it exists below the level of conscious experience. Circadian rhythms regulate sleep, hormone production, body temperature, immune function, and dozens of other physiological processes in a cycle tied directly to the rotation of a planet relative to its star. The cycle is not just cultural, it is cellular. Your body expects the sun to go away and come back. It has been expecting that for as long as your species has existed. Now consider a world where that rhythm never existed. where one side of the planet has been facing its star since before any complex chemistry had a chance to organize itself, and the other side has been facing the dark for just as long. Not a long winter, not a polar night lasting months, a night that has lasted billions of years and will last billions more. This is tidal locking, and it is far more common in the universe than the kind of day-night cycle Earth has. When a planet orbits close enough to its star, the gravitational interaction between them does something slow and irreversible to the planet's rotation, the same mechanism that gives Earth ocean tides. The slight difference in gravitational pull between the near side and far side of the planet operates on the planet's rotation itself. Over millions of years, that differential force gradually slows the planet's spin. The rotation period gets longer and longer until it matches the orbital period exactly. At that point, the planet completes exactly one rotation for every one orbit. One side permanently faces the star. The other side permanently faces away. The moon is tidally locked to Earth. That is why we always see the same face of the moon. The same mechanism applies to many planets orbiting in close proximity to their stars. And close proximity is exactly where the most common stars in the galaxy tend to place their habitable zones. Red dwarf stars make up roughly 70 to 75% of all stars in the Milky Way. They are smaller and dimmer than our Sun. They're habitable zones. The range of orbital distances where liquid water could theoretically exist on a surface sit much closer to the star than Earth sits to our Sun. A planet in the habitable zone of a red dwarf is typically orbiting at a fraction of the distance between Earth and the Sun. At those distances, tidal locking is not just possible. For most planets, it is the expected outcome, given enough time. This means the most common type of potentially temperate rocky world in the galaxy is probably a world with one permanent day side and one permanent night side. 39 light-years away, in the constellation Aquarius, the TRAPPIST-1 system contains 7 planets roughly the size of Earth orbiting an ultra-cool red dwarf star. 3 of those planets, designated TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, orbit within the habitable zone as defined by stellar flux. All 7 are almost certainly tidally locked, or very close to it. TRAPPIST-1e is considered one of the more interesting candidates in the system. Its size is close to Earth's. Its mass and density suggest a rocky composition. It receives a level of stellar radiation that models suggest could allow liquid water to exist on its surface under the right atmospheric conditions. What those conditions would actually feel like is something else entirely. The day side of TRAPPIST-1e faces its star permanently. The star is an ultra-cool red dwarf that emits most of its light in the infrared rather than in visible wavelengths. The light on the day side would look different from sunlight on Earth. Rather, dimmer in the wavelengths our eyes are tuned to. The sky, if an atmosphere exists to scatter that light, might appear in colours with no equivalent in any sky humans have ever looked up at. The night side faces away permanently. No stellar light. No warmth from the star. Only the ambient temperature of a rocky world slowly losing heat to space and the faint light of distant stars. Not a dark night that ends at dawn. A dark that has no dawn scheduled. Billions of years of night. Uninterrupted. Without the reset of a sunrise to warm the surface again. Between those two extremes runs the Terminator line, a band circling the entire planet where the day side transitions to the night side. On a tidally locked world, the Terminator is not moving. It is fixed. A permanent twilight zone running from pole to pole and back again around the entire circumference of the planet. If TRAPPIST-1e has an atmosphere substantial enough to transport heat from the day side to the night side, the Terminator might be the most temperate region on the planet. Not because it receives the ideal amount of stellar energy directly, but because it sits at the boundary where heat transported from the burning day side meets the cold radiating from the frozen night side. A narrow band where conditions might be, in a very loose sense, moderate. A ring of perpetual twilight is the closest thing this world has to a comfortable address. The word might appear in every sentence about TRAPPIST 1e for a reason. The system is real. The planets are confirmed. The orbital parameters are measured with impressive precision. What is not known is what any of these worlds' atmospheres look like, whether they have substantial atmospheres at all, and whether any of the conditions that models suggest as possible actually exist on their surfaces. Red dwarf stars present a specific challenge that goes beyond tidal locking. Young red dwarfs are significantly more active than our Sun. They produce flares, bursts of radiation and energetic particles, at higher rates and for longer periods in their stellar youth. A planet forming in the habitable zone of a red dwarf would be exposed to that radiation during the period when it was also trying to hold on to its atmosphere. Whether rocky planets around red dwarfs can maintain meaningful atmospheres against that bombardment is one of the central open questions in exoplanet science right now. The James Webb Space Telescope has begun observing TRAPPIST-1 planets in transit. Early results from the two innermost planets in the system suggest those worlds have little to no substantial atmosphere, or at least not the kind that would retain significant heat. The question of what TRAPPIST-1e has, further out in the system and in the habitable zone, remains open. Observations are ongoing. The nearest potentially temperate world to our solar system is Proxima Centauri b, orbiting Proxima Centaur, the closest known star to the Sun, at about 4.2 light-years away. Proxima Centaur is a red dwarf. Proxima Centauri b orbits in its habitable zone. Its orbital period is about 11 Earth days. At that distance, and with that period, tidal locking is the expected outcome. The world next door, the nearest planet to Earth outside our own solar system, is in all likelihood a planet divided permanently against itself. One side in perpetual day, one side in perpetual night. No Earth-like circadian rhythm driven by sunrise and sunset. No cycle to organize time around. Just a line running around the world that separates two permanent states of existence, and a narrow twilight band between them where the physics of two extremes meet. TRAPPIST-1e is not a second Earth. It is a question mark, a genuinely interesting question mark, orbiting a star 39 light-years away, with a permanent night on one side and a permanent day on the other, and a thin ring of twilight in between that might, under the right conditions, be the closest thing in that system to a place where something could hold on. It is not a promise. It is a question, and right now, we are building the tools to ask it properly. Everything we have looked at so far has had a star. Even the most extreme worlds, the ones being consumed, the ones covered in molten rock, the ones orbiting stellar corpses, have a gravitational anchor, something at the center of their orbit, something that defines their path through space, gives them a year, a day side and a night side, a reference point for where they are and where they are going. The star is the organizing principle. The Sun is what makes a solar system a system. Now remove it. Not through destruction, not through some catastrophic event. Just remove it from the equation entirely. A planet with mass and composition and geology. No star. No orbit. No sunrise. Just a world moving through the galaxy in a straight line, belonging to nothing, headed nowhere in particular, drifting through the space between stars as freely as a stone thrown into the open ocean. These are rogue planets, and they may be extraordinarily common. The mechanism that produces rogue planets is familiar from earlier chapters. Young planetary systems are chaotic. Planets form in a disk of gas and dust around a young star, interact gravitationally with each other and with the disk material, and migrate. Most of the time, these interactions settle into stable configurations. Sometimes they do not. A close gravitational encounter between two massive planets can transfer orbital energy in a way that sends one of them onto an escape trajectory. It crosses the threshold where the star's gravity is no longer sufficient to hold it. It continues outward. It never comes back. The planet does not explode. It does not change composition. It simply leaves. Rogue planets can also form directly from collapsing clouds of gas and dust that are not massive enough to ignite nuclear fusion. They form like stars but fall short of starhood, ending up as planet mass objects with no parent star, born free of any system from the beginning. Detecting rogue planets is challenging precisely because they have no star to orbit and therefore produce no transit signals and cause no measurable stellar wobble. The primary detection method is gravitational microlensing. When a massive object passes between Earth and a distant background star, the object's gravity bends the light from the background star, causing it to appear temporarily brighter. The shape of that brightening curve contains information about the mass of the lensing object. A rogue planet passing between us and a distant star creates a specific, brief brightening signature that differs from the signature of a full stellar system. Microlensing surveys have found a statistically significant population of these events consistent with free-floating planet mass objects. Some estimates, based on the frequency of microlensing events, suggest there could be tens of billions of rogue planets in the Milky Way, and certain analyses have pointed toward even higher numbers. These estimates carry significant uncertainties, and the true population remains an open question. But even conservative figures place the number of free-floating worlds in the galaxy at a scale that is difficult to process. Consider what it means to stand on one. No sunrise. That is the first thing. There is no direction in the sky that is different from any other direction. The stars are distributed across the sky in the pattern you would see from deep space. No bright, dominant source among them. Just the stellar background in all directions at roughly equal intensities. The sky is never blue. It is never lit. It is the permanent star field of the interstellar medium, cold and uniform and offering nothing that could be called a day. No year. The planet is not orbiting anything, so there is no orbital period. No return to the same position after a fixed interval. No seasons. The surface temperature is determined not by stellar radiation but by the planet's own internal heat, slowly radiating outward from a core that formed billions of years ago and has been losing thermal energy ever since. For most rogue planets of Earth mass, that internal heat would long since have dissipated to the point where the surface is extraordinarily cold, a dark surface receiving no stellar warming, radiating its remaining heat into the interstellar void over geological timescales. Larger rogue planets present a different picture. A rogue planet with the mass of several Jupiters retains significantly more internal heat than a smaller world, and that heat can maintain temperatures in a more moderate range for far longer. Some researchers have proposed that a sufficiently massive rogue planet with a hydrogen-rich atmosphere could maintain surface temperatures above the freezing point of water through the greenhouse effect of that atmosphere alone, without any stellar input whatsoever. The atmosphere traps the heat radiating from the interior. The planet effectively insulates itself. This remains speculative for any specific world, but the physics does not obviously forbid it. PSO J3 18.5-22 is a free-floating, planetary mass object about 6 times the mass of Jupiter, roughly 80 light-years from Earth. With no detected host star, its surface temperature is approximately 1,160 Kelvin, roughly 900 degrees Celsius. It glows visibly in the infrared because of residual heat from its formation. A world with no star, emitting its own faint light from thermal radiation, drifting through the galaxy alone like a cooling ember in a very large dark room. There is a word that comes to mind when you think about rogue planets long enough, and the word is wanderer. The word planet itself comes from the ancient Greek word for wanderer. The Greeks used it to describe the objects in the night sky that moved relative to the fixed stars, the things that did not stay in one place. The sun, the moon, the 5 visible planets. All were called wanderers because they moved against the background. Rogue planets take that original meaning to its furthest possible conclusion. They are wanderers in a sense the Greeks could not have imagined, not wandering across a fixed sky from the perspective of a stable Earth. wandering through the galaxy itself, drifting between stars over millions and billions of years, carrying their geology and their cold surfaces and their slowly cooling interiors through the spaces between the lights that the rest of the universe organizes itself around. They are complete worlds, real, physically substantial, with mass and composition and, in some cases, potentially complex chemistry, and they belong to nothing, acknowledge no star, travel the galaxy as independent objects with no gravitational allegiance to anything. Homeless worlds, with everything a planet needs to exist, and nothing a planet needs to be part of somewhere. Most strange planets are strange because of what they have. Too much heat, too much pressure, too much gravity, too much atmosphere doing things atmosphere was never supposed to do. The extremes we have looked at so far are extremes of presence, of excess, of physics operating at scales that overwhelm the baseline assumptions we brought with us from Earth. This one is strange because of what it does not have. About 750 light-years from Earth, in the constellation Draco, there is a planet called TRES 2b. It is a gas giant, roughly the mass of Jupiter, orbiting a star at a distance close enough that its year lasts about 2.5 Earth days. By the standards of the planets we have already discussed, those numbers are almost unremarkable. Hot Jupiter, close orbit. We have seen that. What makes TRES 2b different is its surface. TRES 2b reflects less than 1% of the light that hits it. 1%. For context, fresh asphalt on a road reflects about 4% of incoming light. Coal reflects about 4%. The darkest natural materials found in any significant quantity on Earth reflect somewhere between 3 and 5%. TRES 2b reflects less than any of them. It is, by the measurements available, the darkest planet ever discovered, a world that absorbs nearly all the light its star sends at it and returns almost none of it back to space. If you could somehow hover above TRES 2b and look down, you would see almost nothing, not the dramatic blackness of space, which is at least honest about what it is, something closer to a void pretending to be a surface, a planet that is present but nearly invisible, even from close range, even under direct starlight. This raises an obvious question. What is it made of? The honest answer is that the exact cause of TRES 2b's extreme darkness is still being investigated. Gas giants in close orbits typically form cloud layers that reflect a meaningful fraction of incoming light, which is part of why hot Jupiters are often easier to study than their distance might suggest. TRES 2b appears to lack those reflective cloud layers, at least at the altitudes where reflected light would be detectable. One possibility is that the extreme temperature of its atmosphere, driven by its close proximity to its star, keeps potential cloud-forming compounds in a gaseous state, rather than allowing them to condense into reflective particles. The same heat that prevents clouds from forming also prevents reflection. Another contributing factor may be the presence of light-absorbing compounds in the upper atmosphere. Vaporized sodium, potassium, and titanium oxide have all been proposed as potential absorbers, materials that preferentially capture incoming photons rather than bouncing them back. The atmosphere becomes a collector rather than a mirror. The result is a planet that takes in radiation and gives almost nothing back, a world that swallows light. There is something philosophically interesting about TRES 2b that goes beyond the strangeness of its albedo. We find planets, generally, because of their relationship with light. Transit detection works because a planet blocks light from its star as it passes in front. Radial velocity works because a planet's gravity shifts the wavelength of its star's light. Direct imaging works because a planet reflects or emits light we can detect. Even the indirect methods trace back, eventually, to photon. Light is the medium through which we know the universe. TRES 2b is a planet that has largely opted out of that relationship. It is there. It orbits its star. It has mass and a diameter and an atmosphere, but it participates in the exchange of light at the minimum level the physics allows. It is present in a way that is almost a refusal to be seen. We found it anyway, because the transit method does not require a planet to reflect light. It only requires a planet to block it, and Strangest 2b, for all its darkness, still has enough mass to cast a shadow. That shadow was enough. But here is what sits with you after you think about Strangest 2b for a while. The planet is not dark because something happened to it. It is not dark because it was stripped or burned or pushed into the wrong orbit. It is dark because of what its atmosphere is, because of the specific chemistry that formed under the specific conditions of its specific orbit around its specific star. The darkness is native. It is the natural outcome of the physics operating on this world. The universe is under no obligation to make its planets visible. It built one that absorbs nearly all the light thrown at it and offers almost nothing in return. And it did this using the same basic ingredients and the same basic forces it used to build every other planet we have ever found. Some worlds glow with internal heat. Some reflect two suns across double shadow landscapes. Some catch enough starlight that we can map their clouds from 1,000 light years away. And some of them just take the light in and keep it. Strangest 2b is out there right now, in the constellation Draco, 750 light years away, orbiting its star in 2.5 days, absorbing nearly everything its star sends at it, and returning almost none of it. A world that has been doing this for longer than human civilization has existed, in a darkness that is not the absence of a star, but the absence of reflection, the darkest thing we ever found. And the fact that we found it at all says something about how far we have come in learning to see. In 1992, 3 years before, Kellos and Mayer confirmed 51 Pegasi b, two astronomers named Alexander Wolszczan and Dale Frail announced that they had found planets orbiting another star. The announcement should have been the most celebrated moment in the history of planet hunting. The first confirmed exoplanets. The first proof that worlds exist beyond our solar system. The discovery that generations of astronomers had been working toward. The reaction was not celebration. It was something closer to unease. Not because the discovery was doubted. The data was solid. Wolszczan had been working with the Arecibo radio telescope in Puerto Rico, timing the radio pulses from an object called PSR-B 1257+12, a pulsar, a neutron star, the collapsed remnant of a massive star that ended its life in a supernova explosion. Pulsars rotate at extraordinary rates and emit beams of radio waves with a regularity so precise that they function as natural clocks, some of them maintaining stability that rivals precision instruments over astronomical timescales. What Wolszczan found was that the timing of the pulses from PSR-B 1257+12 was not perfectly regular. There were tiny, systematic variations. The pulsar was speeding up and slowing down very slightly, in a pattern that repeated with a specific period. And the only explanation consistent with the data was that something was orbiting the pulsar, tugging at it gravitationally, causing it to move slightly toward and away from Earth in a periodic cycle. But unlike the radial velocity method Kellos would use 3 years later, Wolszczan was not measuring shifts in starlight. He was measuring the timing of a cosmic clock. The pulsar itself was the instrument. The planets were the thing making it run slightly unevenly. Not starlight wobble. Pulsar timing. A completely different method. Reading a completely different signal. Arriving at the same conclusion. There was not one orbital signal in the timing data. There were three. 3 separate periodicities. 3 separate gravitational tugs. Consistent with 3 objects orbiting the pulsar in distinct orbits. 3 planets. The unease in the scientific community came from what those planets were orbiting. PSR-B 1257+12 is a millisecond pulsar. It rotates 161 times per second. It is the remnant of a star that died in a supernova explosion. A catastrophic event that released more energy in a few seconds than our Sun will release in its entire 10 billion year lifetime. The explosion that created this pulsar would have sterilized any planets in the original system. The radiation environment around an active millisecond pulsar is extreme by any measure. Gamma rays, X-rays, high-energy particle winds, a continuous bombardment of ionizing radiation that would strip atmospheres and irradiate surfaces at rates incompatible with any chemistry we associate with life. And yet there were planets, 3 of them, in stable orbits around a dead star. The question that followed the discovery, and that has never been fully resolved, is how they got there. 2 leading scenarios exist. In the first, the planets are survivors. They existed around the original star before the supernova. The explosion was violent but not perfectly symmetric, and the planets were not directly destroyed. They were flung into disrupted orbits by the blast and eventually settled into new stable configurations around the pulsar remnant. In the second scenario, the planets formed after the supernova, from the disk of material left behind by the explosion itself, the debris of a dead star, ejected and then recaptured by the pulsar's gravity, gradually accumulating into planet-sized objects in a second act of formation built entirely on the remnants of the first. Both scenarios are possible. Both have been modelled. The data does not definitively choose between them. What the data does confirm is that at least 3 planet mass objects are orbiting PSR B12 57+12 right now, in stable configurations, around a rotating stellar corpse. Consider what existing on one of those worlds would mean. The pulsar does not warm anything. It does not emit visible light as a primary radiation type. It sweeps beams of radio waves and high-energy radiation through space 161 times per second. From the surface of a planet in that system, those beams would arrive like the strobe of a lighthouse operating at a frequency faster than the human eye could resolve as separate flashes. Not a sun, a pulse, repeating before the previous one has had time to register. The radiation environment would make the surface incompatible with the biology of any organism we have ever studied. The pulsar wind, the stream of charged particles flowing outward from the neutron star, would interact with any remaining atmosphere in ways that would progressively erode it. The chemistry available on the surface, driven not by the moderate photon energies of visible light, but by the high-energy radiation of an active millisecond pulsar, would be entirely unlike anything that produced life on Earth. This is a planetary system built on a foundation of violence. The star it orbits did not age gracefully. It exploded. Whatever came before the explosion, whatever history those planets or their predecessors had with the original star, was erased in an event energetic enough to be briefly visible from across the galaxy. What remained kept orbiting, not because it was supposed to, not because any model predicted it, because the gravitational mathematics worked out. And physics does not require permission to produce outcomes that feel inappropriate. WD 1145 plus 017 demonstrates a different version of the same story. A white dwarf, the dense remnant left when a star like our Sun exhausts its nuclear fuel and sheds its outer layers, is being orbited by debris that observations strongly suggest is the remains of a disintegrating planetary body. The white dwarf's gravity is shredding the object. As the debris spirals inward through tidal forces, it transits across the face of the white dwarf as seen from Earth, causing detectable dips in brightness. What the data shows is not a stable planet in a stable orbit. It is a world in the process of being torn apart. The tidal forces of the white dwarf exceed the internal gravity, holding the object together. Piece by piece, orbit by orbit, the object is being pulled into a disk of debris that falls onto the white dwarf's surface. The white dwarf spectrum shows absorption lines from metals, silicon, iron, magnesium, calcium, elements that should not be present in the atmosphere of a white dwarf because they are heavy and should sink below the surface quickly. The fact that they are detectable means they are being continuously replenished. The planetary body is still disintegrating. We are watching, in real time. The end of a world. The white dwarf at the centre of this system is what our Sun will eventually become. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core. It will expand into a red giant, engulfing Mercury and Venus and possibly Earth in the process. Eventually it will shed its outer layers as a planetary nebula, and the core will be left behind as a white dwarf. Roughly the size of Earth, but with the mass of the Sun compressed into that volume. Any planets that survive that transition will continue to orbit the white dwarf remnant. The solar system will not end when the Sun dies. The orbits will continue. The planets will circle the cooling white dwarf for billions of years. If any of those surviving planets are perturbed into an orbit that brings them too close to the white dwarf's tidal radius, what is happening at WD1, 14, 5 plus 017 is what awaits them. The first exoplanets ever confirmed orbit the corpse of a star that exploded. The nearest planetary system we can observe actively disintegrating is being torn apart by the remnant of a dead star. The stellar graveyard is not empty. It is full of planets. This is not the picture of the universe that exoplanet discovery was supposed to produce. The expectation was that finding planets beyond our solar system would reveal worlds of potential. Planètes inhabitables zones. Worlds that might harbour life. The cosmic inventory that might eventually show we are not alone. The first entry in that inventory was 3 planets orbiting a neutron star, spinning 161 times per second, in a radiation environment that would destroy the chemistry of life as we understand it, around the remnant of a star that ended in one of the most violent events the universe produces. Not what anyone had in mind, but real, unambiguously, precisely, observationally confirmed real. The universe built a planetary system around a dead star. It followed the same gravitational rules that built our solar system and produced something that exists at the furthest edge of what those rules can look like when applied to the most extreme starting conditions imaginable. Wolfsjan and Frail found 3 planets. They were not looking for planets around a dead star. They were studying the timing of radio pulses and noticed the clock was running unevenly. The explanation was planets. The universe does not consult our expectations before building things. And the planets, whatever they are, keep orbiting, 161 times per second. The pulsar sweeps its beams across whatever sky those worlds have left. The signal repeating, the orbit continuing, the dead star doing what dead stars do when the physics still has instructions left to follow. 730 light-years from Earth. There is a planet that should not look the way it does. Its radius is close to that of Neptune. Neptune-sized worlds are generally expected to be gas-rich. Neptune itself is composed primarily of water, methane, and ammonia in a slushy mixture under enormous pressure, with a hydrogen and helium atmosphere on top. The density of Neptune is about 1.64 grams per cubic centimetre, heavy for a gas world, but consistent with a planet that has held onto a substantial volatile envelope over billions of years. The planet designated TOI 849b has a radius slightly smaller than Neptune. Based on that alone, a reasonable expectation would be a similar composition, a volatile, rich world with a thick atmosphere and a density somewhere in Neptune's range. Its mass is approximately 39 to 40 times the mass of Earth. Neptune's mass is about 17 times Earth's mass. TOI 849b is more than twice as massive as Neptune at roughly the same size. Its density is approximately 5.5 grams per cubic centimetre. For comparison, Earth's average density is 5.51 grams per cubic centimetre. A Neptune-sized world with the density of Earth is not what any model of planet formation would predict as a routine outcome. Something happened to this planet. The mass is there. The volatile envelope that should surround it is not. The leading hypothesis begins with what the planet is and ends with what it lost. TOI 849b orbits its star at a distance so close that it completes a full orbit in less than 18 hours. At that distance, it receives an enormous flux of stellar radiation. The same photoevaporation process that strips atmospheres from smaller planets operates here, but at a scale proportional to the mass of gas that may once have surrounded this world. The current thinking is that TOI 849b could be a planetary core, not a small planetary core embedded within a gas giant, the way Earth's iron core sits at the centre of a rocky planet. What may be the actual exposed core of what was once a gas giant? A world that formed with a massive hydrogen and helium atmosphere and then lost it, either stripped away by the intense radiation from its close-in orbit, or disrupted by a collision with another massive body, or some combination of both over the system's history. If this interpretation is correct, we are looking at the interior of a gas giant, the part that is normally hidden under hundreds of kilometers of pressurized gas, the dense rocky and metallic core that accumulates first in the standard model of planetary formation before the gas collapses onto it. We cannot directly look inside Jupiter or Neptune. Their cores are buried under pressures and depths that no instrument has ever sampled directly. TOI 849b may be showing us what that interior looks like from the outside, stripped of everything that normally covers it. The implications extend beyond this one planet. In the region of orbital space very close to stars, there is a notable absence of Neptune-sized planets. This region has been given the informal name the Neptunian Desert, not because it is sandy, but because planets of that size are statistically underrepresented at very close orbital distances compared to either smaller rocky worlds or much larger gas giants. The explanation that fits the data best involves photoevaporation. Planets in that size range, massive enough to accumulate a significant gas envelope during formation, but not massive enough to retain it against intense stellar irradiation over billions of years, gradually lose their atmospheres. What remains after the gas is gone depends on what was underneath. If the core is massive enough and dense enough, it persists as a rocky or metallic world at close orbit. If the core is not, the planet may be entirely disrupted. TOI 849b is massive enough and dense enough to persist. It is sitting in the Neptunian desert, not as an anomaly, but as a survivor of the process that created the desert in the first place. GJ 3470b tells a similar story at an earlier stage. It is a Neptune-mass planet that observations suggest is actively losing its atmosphere right now. Ultraviolet observations have detected signatures consistent with ongoing atmospheric escape, a cloud of escaping gas surrounding the planet as it orbits its star. The planet is not a finished object that arrived at its current state long ago. It is in the middle of the transformation. The stripping is happening now, and if it continues long enough, what eventually remains may look something like TOI 849b looks today. We are catching these worlds at different points in the same process. TOI 849b at what may be the end. The core exposed and the envelope gone. GJ 3470b in the middle. The envelope actively departing. Other worlds in the Neptunian desert likely represent the full range of stages between formation, with a complete gas envelope and the eventual stripped core. The picture that comes into focus from these observations is one of planetary transformation on geological timescales. Planets are not static objects. They change. They lose material. They migrate. They interact with their stars in ways that fundamentally alter their composition and structure over billions of years. The planet we observe today is not necessarily what formed billions of years ago. The taxonomy we apply based on current observations captures a snapshot, not a permanent state. There is a quiet implication in this that reaches further than any single planet. When we look at a rocky world orbiting close to its star and classify it as a super-Earth or a terrestrial world, we are making an observation about what it looks like now. We are not necessarily making a statement about what it was. Some fraction of the rocky worlds we find at close-in orbits are not primordially rocky. They are the remnants of gas giants that migrated inward and lost their envelopes. They started as one thing and became another, stripped down by their star over timescales longer than human civilization has existed. The universe does not just create planets, it edits them. It takes something and removes layers over time until what remains is the fundamental structure that was always underneath. Not a new planet. The same planet, reduced to its essential density, its deepest layer. The part that survived the editing process because it was too massive and too dense to be taken away. What we see when we look at TOI 849b is not a broken version of something else. It is the answer to a question we could not ask until recently. What lives at the centre of a gas giant? What is underneath all that hydrogen and helium and pressure? The answer, in at least one case, is a dense rocky metallic core the size of Neptune and the weight of nearly 40 Earths, sitting in plain view in a close orbit around its star, exposed by billions of years of radiation, doing exactly what radiation does to gas it can reach. The bones of a giant, still orbiting, still there after everything built around them was taken away. In 2019, at the Nobel Prize ceremony in Stockholm, Didier Queloz stood at a podium and said something that had taken him 24 years of planet hunting to fully believe. He said that the more planets we find, the more we understand how specific Earth is. Not unique in the absolute sense, not the only possible version of a living world in a universe this large, but specific, particular, the product of a combination of circumstances that the universe does not appear to assemble routinely, and that we mistook for normal because it was the only example we had for most of human history. He did not say it with sadness. He said it the way you say something you have spent a long time arriving at and are finally at peace stating plainly. After everything in the previous 11 chapters, it is worth sitting with that statement for a moment. We have looked at a planet completing a full orbit in 30 hours while its atmosphere bleeds into space. We have looked at worlds where the ground is an ocean of molten rock and the weather is made of vaporized minerals. We have looked at skies moving at 7 times the speed of sound, carrying silicate glass and iron vapor. We have looked at planets so diffuse they challenge our intuitions about what large objects are supposed to weigh. We have looked at worlds where gravity and pressure transform water into states that have no name in everyday language. We have looked at worlds with 2 suns casting double shadows, worlds divided permanently between burning day and frozen night, worlds drifting through the galaxy with no star at all, a world that absorbs nearly all the light thrown at it and returns almost none, and worlds orbiting the dense spinning remnants of stellar explosions. And now we need to look at Earth. Not the Earth of politics or ecology or any of the particular concerns of this particular moment. The Earth as a physical object, as a planet, as a data point in the catalogue of worlds the universe has produced. When you look at Earth that way, after everything, the first thing that becomes clear is that almost nothing about it was guaranteed. Start with the star. Our Sun is a G-type main sequence star. It is not the most common type of star in the galaxy. Red dwarfs make up roughly 70 to 75% of all stars in the Milky Way. Our Sun sits in a minority category by stellar population. It is more luminous than most stars, more stable in its radiation output over long timescales, and burns hydrogen at a rate that allows for multi-billion-year stability without the intense flaring activity that characterizes young red dwarfs. A planet at Earth's distance from a red dwarf would be far outside the habitable zone. Too cold for liquid water. To sit in the habitable zone of a red dwarf, a planet must orbit much closer, which, as we have seen, creates tidal locking, elevated radiation environments, and a range of other conditions that complicate the picture considerably. Earth is in a temperate zone in part because it orbits the kind of star it orbits. At the distance it orbits it, that combination is not the statistical majority. It is a specific configuration in a galaxy where the most common stars are smaller, dimmer, and more active. Then there is the orbit itself. Earth's orbit is very nearly circular. Its orbital eccentricity sits at about 0.017, nearly circular. As a result, The distance between Earth and the Sun varies by only about 3% over the course of a year. The seasonal variation in temperature we experience is driven primarily by axial tilt, not by changing distance from the Sun. Many exoplanets have significantly more eccentric orbits, which would produce much more extreme swings between heat and cold as the planet swings close to its star and then retreats far from it. Earth's nearly circular orbit is not guaranteed by orbital mechanics. It is the result of the specific gravitational history of our solar system, the particular sequence of planetary interactions and migrations that left the inner planets in their current configurations. Then there is the Moon. The Moon is unusually large relative to Earth. The ratio of the Moon's mass to Earth's mass is roughly 1 to 81. Most moons in the solar system are far smaller relative to their parent planets. The Moon is thought to have formed from the debris of a collision between the early Earth and a Mars-sized body roughly 4.5 billion years ago. That collision was specific. A specific angle of impact. A specific relative velocity. A specific mass of the impacting body, all contributing to producing a moon of a specific size. That size matters. The Moon's gravitational influence stabilizes Earth's axial tilt. Earth currently tilts at about 23.5 degrees relative to its orbital plane, and that tilt is what produces our seasons. Without the Moon's stabilizing influence, computer models suggest Earth's axial tilt could vary chaotically over millions of years, swinging to values that would produce climate extremes far beyond anything in recorded history. The stable, moderate tilt we have is partly a consequence of having a large moon in the right configuration at the right distance to damp those oscillations. Mars, which has no large moon, shows evidence of significant axial tilt variation over geological time. Earth's relative climate stability, compared to what it might have been, is partly a gravitational accident produced by a collision that happened before complex life existed. Then there is the magnetic field. Earth has a strong global magnetic field generated by the circulation of liquid iron in its outer core. That field deflects the solar wind, the continuous stream of charged particles flowing outward from the Sun. Without that deflection, the solar wind would interact directly with the upper atmosphere, gradually stripping it away over geological time. Mars likely had a stronger magnetic field early in its history. When that field weakened and eventually failed, the solar wind began eroding the Martian atmosphere. Today, Mars has an atmosphere about 1% as dense as Earth's. The surface pressure is so low that liquid water cannot exist on the surface under normal conditions. The water that once flowed on Mars, evidenced by ancient river valleys and lake beds visible in orbital imagery, is gone. Earth's magnetic field has persisted for billions of years because the planet retained enough internal heat to keep the outer core liquid and circulating. A slightly different composition, a slightly different mass, and the field might have weakened earlier, and the atmosphere might have gone the way of Mars's. Then there is Jupiter. Jupiter's position in the outer solar system and its gravitational influence have shaped the inner solar system in ways that are still being studied and debated. The question of whether Jupiter has acted primarily as a protector, deflecting potential impactors away from the inner planets, or whether it has also sent material toward the inner solar system at various points in history, is one that planetary scientists continue to work through. The picture is more complex than the simple shield narrative that sometimes appears in popular accounts. What is clear is that having a gas giant of Jupiter's mass at Jupiter's location is not a given. Many planetary systems have no equivalent. The presence of Jupiter is part of the specific gravitational architecture that shaped what the inner solar system looks like today. None of these factors, the star type, the orbital shape, the moon, the magnetic field, the outer solar system architecture, guarantees a living world on its own. Each one is a necessary but not sufficient condition. What makes Earth specific is not any single factor, but the combination, the overlap of all of them, simultaneously, on the same planet, maintained over the billions of years required for life to develop from chemistry to complexity. The probability of any given planet matching that combination is not something we can calculate with confidence yet. We do not know enough about how life begins, how robust it is to varying conditions, or how many alternative paths to complexity might exist that we have not yet imagined. The honest answer is that we do not know how rare Earth is. What we do know is that it is not the default. The catalogue of exoplanets does not show us hundreds of Earths waiting to be found. It shows us a vast diversity of worlds, most of them extreme by any measure we apply from our own experience. Hot and close, cold and dark, crushing and airless, flooded and pressurized, tidally locked, irradiated, stripped, orphaned, and in at least one case, nearly invisible in the dark. From the worlds we can currently measure, Earth looks less like the template and more like a specific outcome. One particular arrangement of star, orbit, moon, composition, and gravitational neighbours that came together over 4.5 billion years into something capable of sustaining the chemistry of life long enough for that chemistry to ask questions about other planets. Kellos spent 24 years arriving at this conclusion. He started by finding the impossible. A hot Jupiter that should not have been where it was, by every model available to him in 1995. He spent the following decades watching the catalogue grow into configurations that no one had predicted, and he arrived at the Nobel podium in Stockholm in 2019 with a conclusion that took the entire arc of exoplanet science to reach. Earth is not normal. Earth is what this one specific arrangement produced over 4.5 billion years. It is us. It is real. It is the only confirmed living world we have. The universe is not building backup Earths for us. It is building planets. In the full, chaotic, indifferent variety that physics permits. Some of them happen to fall in conditions that sound familiar. Most of them are something else entirely. We live on the accident. And the accident, as it turns out, is extraordinary. Right now, somewhere in the Milky Way, a planet is completing an orbit in 30 hours. Its star is pulling its atmosphere into a disk of gas that spirals inward. It has been doing this for longer than human civilization has existed. Right now, on a world 41 light-years from here, a molten surface is churning. Vaporized rock is rising into the atmosphere and falling again on the night side. The cycle has been running for billions of years without interruption. Right now, somewhere in the space between stellar systems, a world the size of several Jupiters is drifting in a straight line with no orbit, no sunrise, and no star to call its own. It glows faintly from heat left over from its formation. It will keep moving. Right now, 3 planets are orbiting a neutron star that rotates 161 times per second. Those planets were there before the first human being walked upright. They will likely still be there when our sun begins to change. All of this is happening now, in the actual galaxy we live in, on actual worlds, at this specific moment. We know this because the tools for knowing it exist and are working. The James Webb Space Telescope is currently measuring the atmospheric chemistry of worlds hundreds of light-years away. It is distinguishing morning from evening on distant hot Jupiters. It is observing TRAPPIST-1 planets in transit, looking for the signatures of atmospheres on worlds orbiting the most common type of star in the galaxy. The Nancy Grace Roman Space Telescope, preparing for launch, is designed to find rogue planets through gravitational microlensing at a scale current surveys cannot match. Ground-based observatories are measuring stellar velocities with precision that would have seemed unreachable when Quillos and Mayer were working in 1995. The catalogue of confirmed exoplanets has passed 6,000 worlds, and the number changes every month. Quillos said after the Nobel Prize that the most surprising discoveries are still ahead. He said this not as optimism but as a reading of the pattern. Every time the tools improved, the universe showed something that the previous tools could not have found, and it was always stranger than what the predictions had prepared anyone for. The hot Jupiter of 1995 was stranger than the predictions. The pulsar planets of 1992 were stranger than the predictions. The super puffs, the lava worlds, the iron rain, the rogue planets, the exposed cores of gas giants, the planet that swallows light. All of them arrived in the data before any model had clearly anticipated them. Somewhere in the data that already exists, something is waiting that will rewrite the next chapter. Something that will make a careful person check their work twice before saying anything out loud. The universe is under no obligation to match our intuitions. It built a gas giant that orbits its star in 4 days. It built a world where the ground is in the air. It built planets around dead stars and sent other planets into the dark between living ones. It built all of this using the same physics, the same 4 fundamental forces, the same laws that govern everything we can see. The solar system was not a map. It was one photograph, taken at close range, of one corner of a gallery that extends further than any current instrument can see. And somewhere in all of it, against the full weight of what the universe tends to build when left to its own devices, there is this planet. This one, where the sky is blue because of how light scatters through nitrogen and oxygen, where water falls from clouds and returns to the sea, where the temperature, right now, at this exact moment, is within a range that allows your cells to function. You ended up here, out of everything the universe was willing to make, out of every lava world and rogue planet and dark-absorbing giant and pulsar-orbiting survivor. You ended up on the one that is gentle enough to hold you. That is not nothing. That is almost everything.